So the last thing we need to do this semester is to shift from talking about limits of functions as something that exists only at a single point. And we want to think about what kinds of functions can we have at which the limit exists not just at one point, but we can show the limit exists at a lot of different points. Ideally, we'd like to show that the limit of a function exists everywhere on its domain when that's possible. And what we're ultimately sort of working our way towards is the kind of argument that we made up here. Right? We'd like to know what we can say about a function when these two things, the limit of the function near a point and the value of a function at that point, are both telling the same story. So those are going to be the objects of study for us for the rest of the semester. So I want functions, I want f's that have, let's call it nearby behavior, as measured by the value of the limit. So the limit has to exist and have a real number value. And I want functions for which that nearby behavior is the same thing as the value of the function at that point. So in other words, what we want for the rest of the semester is we want functions for which the limit of f of x as x tends to a is the same thing as the value of f of a. So this is the holy grail. These are the kinds of functions for which this back-of-the-envelope work that we did up here, where we sort of looked at this function and said, well, why does 6 make sense as the limit? It would make sense as the limit if two things were true. If the value of the function at 3 were equal to 6, and if these two stories, the nearby story and the at story, told the same story. Right? If we knew that the limit and the value agreed, then we can compute the limit by computing the value. And that's what you were doing back in calculus when you would compute one of these limits just by stuffing the number 3 into the function. Right? You're there making the assumption that the limit and the value are going to tell you the same thing. So we want to unpack that assumption and figure out what we can say about those kinds of functions for which that is true, that the limit exists and is equal to the value. Those are the functions that we call, what do you think we call them? Yeah, we call them continuous. And you called them continuous when you met them in calculus as well. And I don't have enough room to write the word continuous, apparently. There we go. So that's going to be our working definition for the moment for continuity. Okay. A function is continuous at x equals a. Let me decorate this a little bit. A function is continuous at the point x equals a if the limit as x approaches a of the function exists, and furthermore, that limit is equal to the value of f of a. In other words, if plugging in a into my function is going to give me the same answer as taking the limit of that function as x tends to a. To finish, we're going to take a step back and think about what kinds of sets of real numbers does the domain of a function, should the domain of a function be, put it that way, in order to be able to make the conclusion that continuity, continuous functions, actually exist. When we were first talking about continuous functions, so when we first talked about continuous functions, just giving you an opportunity to recall what it was that makes a function continuous from calculus, there was this notion that if a function is continuous, that means that we can draw its graph without ever lifting our pencil. So the idea there is that somehow this graph, the graph of f of x, should be just some bendy version of the real number line itself. Somehow the density of points along this graph, if you like, needs to be the same thing as the density of points along the real number line. We can't have any gaps, even if they're somehow infinitesimally small little gaps. We don't want that to happen. So those properties of the graph, when we draw it, it needs to be just as easy and smooth to draw the graph as it would be just to draw the number line itself. Right? And so that's the definition that I want to unpack a little bit, because that's the kinds of sets that our domains of functions need to be in order to make continuity make sense. So maybe the first observation that we can make here is if we want the graph to be just as smooth and unbroken as the real numbers themselves, then one thing we need to be able to do is we first need to be able to define the limit as x approaches a of this function. And so the lowest bar that we want to clear, in order that this limit makes sense, in order to apply this definition, what kind of a point does A have to be? According to what we were talking about last week. In order to satisfy the definition of the limit of a function, remember, we needed to have assurance that however close we need to get to x equals a, we can find a point of the domain of this function. In fact, infinitely many points because of the density theorem. Right? So we needed there to be infinitely many points of the domain of this function arbitrarily close to x equals a. In other words, a needed to be what kind of point? Starts with an a. Yeah, I don't have room to write it all, but accumulation point. Yeah. So in order to be able to define this limit at all, we need for a to have been an accumulation point. So that within any arbitrarily small distance of a, there are infinitely many points of the domain of f. So that will allow us to get as close to a as we would ever need to get in order to make f of x as close to L, the limit, as it needs to be. So that's the minimum bar that we need to clear. But in order to get this notion of unbrokenness across, we also need to avoid something else. So here's another idea. Would we say, so here's a function that's going to, I think, challenge why having an accumulation point is not going to be enough for our notion of continuity. The Dirichlet function defines f of x differently depending on whether x is a rational number or whether x is an irrational number. So already this is kind of a weird piecewise function. But it's going to be defined for all reals because every real is either going to be rational or irrational. So this will define f of x for all real numbers x. And all it does is it assigns a different value for f of x to the real for the rational x's versus the irrational x's. So it'll be 1 for the rationals and 0 for the irrationals. So if I give this function 2/3, it's going to spit out 1. If I give this function square root of 2, it's going to spit out a 0. So this is like a rationality detector function, sometimes called an indicator function in analysis. So what would the graph of this thing look like? So I give this 2/3, it spits out 1. I give this thing square root of 2, it spits out 0. What would the other points on this graph look like? So all of my rational numbers down here on the x-axis, all of my rationals, I'm going to kind of draw them as though they're a sequence of dots, but you get the idea, right? We know from the very beginning of the course that the rational numbers are dense in the reals. And so we would get a whole bunch of 1s in my graph up here. But then the irrationals are also interspaced down here among the rationals. I'll draw them in green. And for all of those irrationals, r minus q, there, the value of this function would be equal to 0. So this graph has kind of a rational number infinitude of these purple dots up here at the number 1. And it also has this irrational amount of infinitude of zeros down here on the x-axis. So the question I want to leave you with today is, would we say that this is a continuous function? Can we draw the graph of this function without lifting our pencil? Probably not. In fact, it'd be really hard to draw this graph without putting your pencil to paper at all, because it has to infinitely many times kind of jiggle back and forth between 0 and 1, right? And yet, I can't actually kind of draw a vertical line because then this wouldn't be a function anymore. And every number is either rational or irrational, so this graph is still going to pass the vertical line test. So this is a really strange graph to think about, but it is a well-defined function for all real numbers. And yet somehow it's not continuous. Somehow we want to say it's not continuous anywhere. There's not a single a value at which we can satisfy this definition. And yet, every point of the domain is in fact an accumulation point of the domain. So that's the bind that we find ourselves in, that is going to necessitate something a little bit more. So every x in the domain is an accumulation point. But f is nowhere continuous. At least that's what we'd like to be able to show. So we need a little bit more expansive of a definition of what kinds of points that we want continuous functions to exist at. Those will be the points that we call interior points. And interior points together make up open sets, and those are the kinds of sets that we want to define continuity on when we return to this narrative on Wednesday.